All right, so the last test that we have to look at, hypothesis test, as far as this particular chapter. So it's variance and standard deviation, which will come from your chi-square. And so that's where we're going to have to look for our critical values, because that's, that's where your variance and standard deviation is. And remember, this one is a little different from the other ones because normally we're using variance and standard deviation in our little formula to find our critical numbers. Well, now we're still going to do that, but it's going to be a little bit different. So we're going to determine the critical chi-square value for a right-tailed test. All right, so we know that we're looking for something like this. It's right-tailed. And we know n is 26 and alpha is 0.1, meaning what's in there? What's in that shaded red area there? 10%, right? And so then over here is obviously then 90%, right? Because it's just one-tailed. But the key to remember with chi-squared is, yeah, n's 26, then, yeah, we have to use 25 because what's that called again? Degrees of freedom. Because again, and it is helpful to know what that means, is they're saying those other 25 values can be whatever, but that last one kind of has to make things work out. And so that last one doesn't have a choice, but the other 25, whatever. All right? And so what you're going to do is find that spot on your chi-squared. So we got degrees of freedom, 25. Notice I gave you a bunch of them to see if you remembered which one to look at, right? So I put 26 on there just to see if maybe you would look at that, all right? So now where do we have to look, though? Obviously, you told me degrees of freedom, so you remembered that. And so we're looking at 25, right? But now what I have to do, remember that chi-squared gives you the area to the right of that value, right? So what value am I going to use? Am I going to use the 0.9? No, you don't use 0.9, right? Because 0.9 would be, well, I better not do it in red, that might confuse you, would be basically that, right? That would be 0.9, and that's not what I want, because that would be 90% to the right. I want the one that says 10%. And so you go to 10%, and now I ruined it. But. And where do the two come together? At 34.382. So here's how you would probably write it. Chi-squared, we're used to right and left, but we don't have right and left this time. So how have we been denoting critical so that we don't confuse it with our statistic? Little zero down there at the bottom, right? So that's our key number that we're looking for, which in this case is 34.382. So if I got a chi-square statistic of, say, 40, can we reject or not? Because it still goes 0 on over. So if I get a chi-squared of like 40, I can reject. Chi-squared of 20, no, very good. Because what it's saying, if I can get my picture back here, and that's one of the different things about chi-squared is it does start at 0, where z and t, 0 is kind of, well, t starts at 0, but in the z's, it's 0's in the middle, where here, 0's over here for a chi-squared. And so they're saying to get way over there, I got to go way over to 34.382. So 40 would be over here, 20 would be over here. So you get it? That's how that works. Okay. So that's if it's a right-tailed test, and we still figure out that the same way. Look at the null hypothesis. It points in the direction of which tail it is. Yes? Yes? Right. That's where we're going to get a chi-squared right and a chi-squared left. Yep, very good. Okay. The question was, can it be two-tailed? Yeah, all hypothesis tests can be right, left, or two. And it's all determinant on the alternate hypothesis tells you which one it is. Okay, if it's pointing to the right, it's a right tail. Pointing to the left, left. If it's a not equal to, then it's 2. Exactly. We won't have any negative z-scores or anything like that. Yep. All right. So now this is a left-tailed. So will this be a negative? This kind of is the same question that was just asked. Will this be negative? No, because it goes 0 on over. All right. These are always positive. Okay. Because remember, this is talking about variance, which we always do what to? We always square, and so there aren't going to be any negatives here. And so, like you told me before, we got degrees of freedom now. So that's 10, right? Now our alpha is much smaller this time. So I want to figure it's a left tail, right? So how much is in there? Only 1%, right? Which means how much is over here then? 99%. Okay. So what value am I going to actually have to look up in this table? Yeah, 0.99, right? Because it says to the right. That's how this one works. I made that really small, huh? Anyways, you can kind of see it, right? Or you have your own table, right? So we're going to go to 10. So that's this one right here. And 0.99 because 99% to the right. So does it make sense that this critical value is much smaller than the first one? Well, because it's to the left side, right? And so chi-squared critical is 2.558. So any questions on that? Okay, so then two-tailed. Yeah, none of them are going to be negative, which was a great question. But we are going to have two of them. Yeah, and so we got, and I hate to keep doing this on you, but I think this is helpful and very important. You can kind of see, what's going on. So how much, especially on two-tailed, it's normally, yeah, very good. It's because it's really 1% total, right? So this is 0.5%, right? Otherwise known as 0.005, right? See, because you got to move it twice, be 0.5%, right? If you move it into decimal form. And degrees of freedom here is 12. Missed it. There it is. So obviously you knew it was 12, so I didn't even bother. But now what you have to have, chi-squared right, chi-squared left. Because this is how we always did them last chapter. We always did two-tailed. Because really they're kind of the best anyways, but because it's at least as extreme, at least as extreme. So chi-squared right is normally the one I look for first. I don't know why, but I just do. So basically, I think it's easier because I know how much has to be over there. Over there has to be 0.005, right? So I go to 0.005, and I go to 12, and I find that it's... Remember, all these different degrees of freedoms are on here because all of these graphs would actually be different. If you actually graphed each one of these distributions, they'd be a little bit different. And so that's why we need all of these values. So in other words, this value right here is 28.3. And then we got to go find that value over there, which is chi-squared left. And so how do you do that then? That's the tricky part. Yeah. 9.995. That's why I like how symmetric this one is, because you can kind of, if you find the right one, you know where the left one's going to be. You know what I mean? If the right one's way over there, the left one's got to be way over here. Okay? Or just think of it this way. That then 99.5 would have to go from there on over. So 3.074. So any questions? Because let's face it, if you can't find the critical values, you're not going to be able to get the right rejection region. So we better make sure everybody's on the same page right now. Would be good? Make sense? Obviously your table's a little bigger than mine, but I just pulled off the ones I needed. All right, well, if you can do that, I think we're set. All right, so here's how you basically, what I'm saying, is this how you find out, does anybody remember from last chapter what it is? That's a long time ago, I know. How do you actually find that statistic, chi-squared? I know the distribution and I know how to find the cut scores now, but how do I actually find that number, what it actually is for my problem? It is n minus 1, very good. Yeah, I was close, s squared over sigma squared. And remember what that is it's saying, yeah, there's your degrees of freedom, and really what is it really comparing? S squared is what? Close. S is sample standard deviation. S squared is sample variance over population variance. So really it's a comparison of the two numbers, because I really would like it to be really close to, that relationship to be very close to 1, because then it's just going to be my degrees of freedom is going to be my answer. Right? And that's kind of what we want. And so we know if we get really close to that, we're doing very good. Okay. If we don't, well, we got some work to do. Or maybe we'll reject. Who knows? Okay. So that's how I gave you all that word, right? You just had to put the formula in, right? Okay. Oh, well, let's give it a shot. So a dairy, I spelled that right? Yeah, okay. I didn't have a dairy processing center. Claims that the variance of the amount of fat and whole milk processed by the company is no more than 0.25. You suspect this is wrong and find a random sample of 41 has a variance of 0.27. So what's the one thing I haven't really said here? Do we need a minimum number, or does NP and NQ have to be anything here? No, because that chi-squared table's got all the information you need. All right, you get it right out of there. So is there enough evidence to reject the company's claim? So right now, before we even get started, you should know where the claim's going to be, just by thinking backwards. Is the claim going to be in the null or the alternate? It'll have to be in the null if we're going to reject, right? And unless I was tricky and I put it somewhere else, and then you say you can't do the problem, right? But we should know that it should be here, right? Unless we do, did something wrong or I was tricky or something like that. So this company says is no more than 0.25. Sometimes that's tricky, yeah. So very good. I think that's the hardest one when they give you the wording like that. I think it's the hardest kind. 0.25 and variance. So what do I got to write then? Sigma squared. Yep. Okay. Sigma squared. Well, that's what they're saying. They're saying if they took the entire population, that's what it would be. All right. Okay. And so then, yeah, this one's got to be everything else, right? And so we know right now this thing's right tail. All right. And I know that you think this is probably silly, but I actually do draw this every time. I draw it in there and I say, okay, here, where is it? It's over there. And so now we have to find out what's our critical value. And I don't have to do right and left. I mean, if you wanted to put right there, I'd basically be okay, but you don't really have to. And so what am I going to look up? So how much alpha is 0.05, which means how much is right there? 5%, right? And degrees of freedom is 40. Okay, so what is our critical? So here's 40. We actually do we look at 95 or do we look at 5? Yeah, let's look at 5, right? Which is 0.05. So it's right here, 0.05 and 40, right? So 55.758. So that's out there a ways, right? But remember, the higher the degrees of freedom, the better this distribution gets. Well, now we got to find out. Which means let's go find it. So it's n minus 1, which you should always have right away. You should just know that number, right? Because you had to do it to find the critical number, right? So it's 40, or your degrees of freedom. Now here's a spot where a lot of people make a mistake. It's s squared, and is that something I know? It says that this sample has a variance of 0.27. So do I put 0.27 squared, or do I just put 0.27? Yeah, it's just 0.27, because that is the variance. You don't have to square it. And that's the biggest mistake people make. Just because there's a square in that formula doesn't mean you have to square it if it's kind of already been done for you, which this one has. And it says that they think the variance is 0.25. So just think if you actually did square this top one and not the bottom one, you think you could have some serious problems, right? I mean, that's not going to be very good at all. Okay. It all depends. Sometimes you get standard deviation, then you do have to square. You got to get to variance on both of them. And how we doing? That 0.27 and 0.25, boy, those are pretty close, aren't they? Then I'm going to take it times 40, though. So do I have a shot at least getting up towards 55 somewhere? Maybe, right? So we at least have to do it, right? And so I got, when I got it, yeah, 43.2. So we had a shot, but it was pretty slim, right? Because we knew these two were pretty close to 1, and I was going to take it times 40, so the chances of getting all the way out to 55 probably weren't very good. And so what that means is we forgot to put where the claim was, right? The claim's right here. We talked about it, but I didn't write it down. So I do not have enough evidence to reject the null, which means I don't have enough evidence to reject the claim at a 5% level of significance. So any questions on that one? Not too bad. Once you get this hypothesis testing down, it's really not that bad once you get the idea. It's almost as if the first section's the hardest one to figure out. Restaurant claims. The standard deviation. Okay, so this is standard deviation, something to make a note of. And the length of serving times is less than 2.9 minutes. That'd be nice. That's pretty low, right? A random sample of 23 serving times has a standard deviation of 2.1 minutes. So that's pretty low. At a level of significance of basically 10%, is there enough evidence to support the restaurant's claim? So again, we should be smart enough to know where that's going to be. Exactly. Yeah, it's got to be in the alternate. So we know standard deviation. So we're saying just sigma this time, right? And they're saying that is less than 2.9, right? And there's our claim. So this must be greater than or equal to 2.9, right? Yep, so it's a left tail. And in that tail must be 10%. So before we even go to it, what number am I actually going to be looking up on this thing? Yeah, we're going to be looking up that 0.90 because it's 90%, right? So we got to look up 0.9, and our degrees of freedom is 22, right? Because 1 less than n. Okay, so here's 22, and you're telling me to look up 0.90, which I agree because it is on the left side, so it should be the smaller number, right? So I get 14.041. 14.041. So now I got to go find out, does this thing even have a chance? So let's actually find out chi-squared for this particular sample. Well, you take n minus 1. Now, do we know s squared? No, we know s. S for this sample is 2.1. So we got to take 2.1 and square it. So that's why I like the two examples we had. That first one was such a small number, you almost thought you had to square it, right? Well, this one is bigger, and we actually do, all right? That's what you got to do. And because we were given standard deviation is, what, 2.9? Do I leave that as 2.9? No, you got to square that one too, right? Okay. So that's why I like these first two examples. They really make you think, okay, well, what information do I have? Do I have to square it, not square it? What's going on? And seeing 2.1 is less than 2.9, we believe that it at least has a chance of, right? If this was, say, 3.0 here, we would know that we really probably didn't have much of a chance, right? But it's 2.1 and 2.9, so it does actually have some possibility, right? In fact, with that being standard deviation, that is pretty far away. I know you think it's only 0.8, but it's pretty far. What'd you get for a chi-squared statistic, chi-squared number? 11.54 is what I got. Which means, now wait, what's this number right here? That's 14, right? 11 is over there, right? 11.54 is in our rejection region, so we can, there's enough to reject the null, which in this case means there is actually enough evidence to support the claim at a 10% level of significance, though. You realize if I change that number, this could change in a hurry. But if that's all the more significant they want it to be, I can actually support the claim this time. Okay? Yeah, that's the tricky part. You got to remember where 0 is. And remember, in a t-distribution, you kind of have those issues, too. You got to kind of, because the t-table only gives you the positive, you have to know if you need the negative or not. Right? That's the difference between that one. But that actually is at 0 in the middle as well. It's just you got to know your positive, negative. Okay? So why don't you take a second or two? Are there any more questions on this one? Because I think you get the idea. Why don't you give the, I'm pretty sure you know what kind of tail it's going to be, too. So I would guess, yeah. So give it a shot. I think it'll be good to see. Do you square it? Do you not? You know, keep it all straight. Remember, there's no minimum on n, really. So, well, it has to be more than one. You know. All right, let's see how you did. It sounds like I think I heard the right answer out there. So, again, you always want to start with this. Sometimes it's easy to want to skip this step, but it's helpful when you get done to not forget what you were trying to do at the beginning. So what are we talking about here? We've got variance this time, right? So we got sigma squared. And what are they saying? It's got to be, what, equal, right? 15.9, and so then down here we're going to say no way, not happening. Now where's the claim actually go? Well, yeah, if I want to reject, hopefully it's the null, right? And that's actually where it ends up being. All right, and so this is, as I kind of mentioned earlier, is going to be 2 because that's the one we haven't done yet. And so we've got 2 of them to find. There it is. And let's see. What's our degrees of freedom here? 14? Yep. And what's alpha? 0.05. So 5% total, so 2.5 on each side, right? And so what? 26.119 right here. And the left one then must be 97.5 basically, right? If you're going to pair it up. So yeah, I probably shouldn't cover up the answer. 5.629. Any disagreements so far? So this is basically, if you think about it this way, this is just the setup. And then you actually have to go get the information. Because you could just go get the information, but it wouldn't mean anything, right? And so what do we got? 14. Now, do we square it or not? No, it already is, right? And so what did they say they got? 21.8? No square in it because it already is, versus what, 15.9? So before even doing this, which one am I going to actually try to get into, the right rejection region or the left? Just by looking in general at the numbers. Right is the only one we have a shot on, right? The S is bigger than sigma. So it would have to be right. If you're trying to hit left on that one, you're not going to do so good. And it stands to be that it possibly, right? To get to 26, just looking at the numbers, maybe. All right. And unfortunately, though, I got, what, 1919? Is that what you got? And so remember, this number here is 26.119. That's your 5 points. So 19's kind of in there-ish, right? And so unfortunately, not enough evidence to reject the null, and so not enough evidence to reject the coin. It's on the verge, though, but not quite. And in fact, if you quickly look at the chart and look at the few other values, there's not much we can do to make that one happen. Because you're not going to go to like a alpha of like 0.25 or something like that. That's not even worth doing the test. Okay. Any questions?